Hello everybody. In this lecture, we'll talk about modeling with first-order equations. So differential equations appeared a lot in applications. Those applications could be anywhere in science, engineering, social sciences, economics. If you want to especially understand how some quantity changes in time, you often run up into differential equations. So that happens in many different subjects like electric circuits, dynamics, aerodynamics, gravity, fluid flow, finance, and this is just to name a few. Okay, in this lecture, we'll start from the simplest possible such scenarios, some simple situations which can be modeled by first-order ODEs. Okay, so there are some key steps when we do this modeling. Maybe the foremost and most important one is determining the dependent and independent variables. And also to give them names if necessary, like attaching some letters to them. Then we should somehow understand the description that relates the rate of change in the problem to the other variables. So relating rates of change of the variables to the variables themselves. That's the step of writing the differential equation. And of course, you want to solve it, but let me not write that. Also, you have to keep an eye on possible additional conditions, such as initial conditions. So, determining initial conditions. These are the key things that you almost always have to do in any such problem. Okay, so I want to directly talk about various examples from several different fields so that we have a sense of more than one of them. Okay, now the first one is about physics, and maybe some of us already know what I'll describe, but in the differential equation setting, it might be nice to review. If you haven't seen this before, I think I'll define all the necessary terms. So say we have some particle moving in space, in three-dimensional space. So its coordinates at time t, I'll denote them by some letters. I need one letter for each coordinate, xt, yt, zt. And if we think about each coordinate separately, these are functions of t. Okay, now let's simplify the problem. Suppose that this particle moves in a way that y and z don't change. So say y and z don't change. So the particle really moves along one dimension. So y and z are constant. We'll not think about them. Only x will change, and we'll just talk about x. Okay, so this x of t denotes the position of the particle in time. Let's say this is the x-axis. Let me forget about y and z. Okay, the particle is gonna move. It will start somewhere, maybe not 0. I mean, this could be some x at t0, the initial position. It can move back and forth, maybe back again. Okay, it's moving in one dimension, but just to emphasize, it's the times that it turns back and forth, I am drawing it like this. Well, okay, this is kind of describing motion. And if you wanted to make a graph of x with respect to t, then you would have something like this. At time t0, it would be at some point x of t0. Then according to this pattern, the graph would be something like x increases, and at some point, at this point, it decreases back a little bit, then begins to increase again further, and from some point when it decreases, maybe it doesn't come this far. Or maybe I should make this longer. Anyway. Okay, so the top diagram describes the motion, sort of, and the graph is graph of the function x with respect to t. Okay, now the rate of change of the position is something which is used in physics a lot. That's the velocity. Its definition is, okay, vt is simply the time derivative of the position. And there's also one more quantity which is very important, that's acceleration. At, that's the time derivative of velocity or second derivative of position. These are definitions. Now, the importance of these quantities comes from classical mechanics, and maybe more specifically Newton's law of motion. There are several laws of motion of Newton, and one of them says, second law should be, I guess, it says that an object is accelerated in a way proportional to the total force that acts on it. That's something you might have seen before as F equals m times a. So force is directly proportional to the acceleration that it gains, and the proportionality constant is mass. So this is some attribute of the object. Okay, so that's why A is important. You usually have some idea about what the force is, so that tells you what the acceleration is, and you have to find the position back. So, well, this is maybe a little bit oversimplified, but we'll talk more about it. Okay, so this is A in terms of the force. So if you want velocity in terms of force, then the same equation says V prime equals F over m. There's a differential equation now. The derivative of V is related to F, and similar for X, right? So then you need a second order differential equation. So you see that differential equations will come up naturally. Okay, now, of course, if you actually want to find these quantities, you have to have a setting where you know something about the force. Now, that might be very different from one example to another. So assume that now that f is constant. That's the simplest thing maybe I can think of. Well, this could be, for instance, the case if your object is freely falling near the surface of the Earth, then this f is equal to, again, mass times the gravitational constant, mg. Okay, in that case, these differential equations are quite easy to solve. Okay, a is f over m is constant. In that case, then you have v prime equals a, and okay, this is a differential equation, but it's really like calculus because you can directly integrate. This is then v is v at t0. This should be v of t. Let's stick in a t here. V of t equals v at time 0 plus integral from t0 to t a dt. This is just a fundamental theorem of calculus. Vt minus vt0 is equal to the integral of the derivative from t0 to t. Now, if a is constant as assumed, this integral will simply be a times t. I should be careful. This is a t, but the t of the integrand. Then I should evaluate at t and t0, so it should be t minus t0, right? Okay. Now it's essential here that a is constant. If a is not constant, then you cannot integrate a like this, then you would have a totally different situation. Now, if you want to find x, you can integrate once again. We know that x prime is v by definition. So x is then, let me do the same thing, x of t is equal to x of t0 plus integral t0 to t d dt, right? Now, fortunately at this point, we know what v is. Okay, so it's now a matter of integrating this quantity. From the vt0 term, which is a constant, you'll just have vt0 times t minus t0. Now, a times t minus t0, this is not a constant anymore. Its antiderivative is t minus t0 squared over 2. That's actually what you get. Okay, so we have a nice and clean formula for x. You could substitute a equals f over m and get everything in terms of the force. You might have seen this formula in a previous physics course, either in first year or in high school. It is the solution of a differential equation, but a simple one. I mean, where a differential equation where the right-hand side only depends on t and not x. Okay, now let's change this situation a little bit. So say we have xt's as before. But suppose that the force is not constant. The force is some F0 minus some constant times the velocity. Okay, might sound a bit strange. So the force is not constant. It is rather some constant force minus some other constant factor times the velocity. Since velocity changes in time, the force also changes in time. So F0, K are constants. Now, this is some situation which we can easily think about in physical terms. The example I want to give is free fall with air resistance. Now, this could be some model like that. Why? You have some particle falling. Well, if it is falling without a resistance, then the force on it is m times g. But now, if there's air here, you'll have some opposite force that opposes the motion, right? So you can think of this mg like the F0 above. And this opposing force is assumed to be, this is not a physical fact, this is just an assumption, a model. It's assumed to be directly proportional to the velocity. Okay. Now, this is partially realistic. I mean, this opposing force being dependent on velocity is somehow realistic. I mean, if you're falling in air, then the faster you are, then you would hit more air molecules per unit time, and that would create more force. So it is kind of intuitively clear that this force is going to be relevant to velocity. Assuming that it is directly proportional, k times v is a strong assumption. And if you want more realistic models of free fall, that's not quite correct. You should put some square term of v or something like that. But anyway, this is nice and simple enough to think about for this problem. Okay. Now, what changes then is your MA is now not constant, it's F0 minus K times V, right? So your A is F0 minus K times V over M. The right-hand side involves velocity. Now, the acceleration itself is the derivative of velocity. So if you write everything in terms of velocity, then you get a nice differential equation. So dE, it is first order linear and also at the same time separable. This is because F0 and M and K are all constants. Okay, so it's not difficult to solve. You can use the techniques from separable equations. You can do this. Now integrate both sides. Is natural logarithm of F0 minus kb this should be equal to 1 over m times t. Actually, I could be a little bit more careful and really put boundaries here. So this could be from some t0 up to t, and here I put the corresponding initial velocity, and this is the variable v of t. So then I have to put these boundaries here. It might be a little bit cleaner to do this with some dummy variables here instead of t. But anyway, this is going to give you ln f0 minus kv minus ln f0 minus kv0 equals t over m minus t0 over m. Okay, we could do some simplifications here. First of all, the difference of two ln's can be rewritten as a ln of the ratio. Okay, I think in the integral I forgot something. I forgot a minus 1 over k. So not here. Here I should add a minus 1 over k, and that goes all through here. Okay. And on the right hand side we have t minus t0 over m. Now this can be further simplified. You push this factor on the right side, and then you exponentiate. That gives, let me do two steps at once. Okay, this is minus k over m times t minus t0, all exponentiated. And from here is some arithmetic to solve for b. Let me write the final answer. Please check it yourself as well. Should be f0 over k plus v0 minus f0 over k times this decaying exponential. Yeah. So the formula that we got is much more complicated than the constant force case. I mean, so if you are falling with a resistance, then you can still get the final answer in a closed form, but this time the formula is much more complicated. It is not just a linear polynomial. You have some decaying exponential, right? So this term is a decaying exponential. Okay, this tells us something. If I take t all the way to plus infinity, and I want to know what happens after a long time, and this decaying exponential part will go to 0. Therefore, you'll be only left with f0 over k. So you have a fixed limit, and this is called the limiting velocity. Okay, so this f0 over k is the limiting velocity. Okay, the important thing here is, okay, something complicated happens here, but as t goes to infinity, that second term goes to 0, and the velocity goes towards some fixed limit. Okay, now let's do another example of a different type. So this one is going to be about population dynamics. Okay, so populations of species change in time, and that might be in quite complicated ways. If you're talking about something like some small populations, I mean populations of small things like insects or even bacteria or a virus, then at the initial stages, the model could be quite simple. So a simple model is about exponential growth. So suppose that the rate of growth of a population of some species is directly proportional to the existing population. Okay, this is a strong assumption. Well, it's saying something like, okay, the bigger population you have, the more offsprings it has, because there are more members of the species to reproduce. So the rate of change of the population is also proportional to the population itself. So now, how do you write a differential equation for this? First of all, we need variables. So let t denote time and pt population at time t. Okay, so this sentence says that the rate of change, therefore dp dt, is some constant times the population itself. K is some constant. If you want to find a constant, you might have to do some observations about this population and see. You have to have some snapshots of the population at some time. So let's try to solve this equation first. So solution is quite simple. This is separable. We have dp over p equals k dt, and you integrate. Okay. This integral is from t0 to t, and this one is from some initial population p0 up to p. The integral on the left will give you ln p over p0, and the integral on the right will give you k times t minus t0. If you solve for t from here, you see that p of t is equal to p0 times e to the power k times t minus t0. So let's double check. So at time equals t0, this exponential term is 1 because it's e to the power 0. Therefore, the population at time 0 is really equal to p0. As time increases, this is exponential growth, right? So if this model would be valid for all times, then this population would grow indefinitely and very fast because exponentials grow very fast. Of course, this will not be a realistic model in the long time range, right? So this model cannot be realistic in long time range because we know that whatever population you have, even if it's a virus, right, after some time, it's out of resources, right, out of space, out of food, or out of people to infect. I mean, out of the resource to grow more. So then what you have to do is you have to change your model. So our original equation was this one. So the population grows in a way directly proportional with the existing population. Now, suppose that when it grows a lot, there is a balancing factor. So we need to put some minus, and we need to put here something which is small compared to Kp when population is small, and large compared to Kp when population is big. So the simplest thing that comes to mind is something like this. Some number times p squared, because the square of p is large compared to p when p is large. The square of p is small compared to p when p is small. Well, think about fractional numbers like 0.01. Its square is much smaller, right? So in that sense, this makes some kind of sense. This is called the logistic equation. Logistic equation. It's quite popular in population dynamics, and even though we kind of put the simplest term possible that we could think about, this does a good job. I mean, so this model really explains many populations in a nice way. Of course, there are more advanced things that you have to consider if you involve more factors, but this model is not bad at all. Okay, so how would you solve this equation? Let me say a few words, but leave the rest to you. This is again separable, right? So if you want to solve it, you would do this and find out this integral. You'll need partial fractions here, and then work out what p is. So do as exercise, please. But let's also think about the direction field for this differential equation. Now, let me rewrite the equation here again for space reasons. So here's the t-axis, p-axis, and your differential equation was dp dt equals kp minus l p squared, which we can also write as p times k minus l p, right? Okay, what's the direction field gonna look like? So remember how we draw a direction field. We will look at the right-hand side values, and at as many points on the PT plane as possible, we put small line segments whose slopes are the values of this function on the right. So this right-hand side only depends on p. So the t value will not matter much. For a fixed p value, if I change the t value, I'll get the same slope. For instance, for p equals 0, this right-hand side is going to give 0, and 0 means horizontal line segments. So I have horizontal line segments at 0. Likewise, at p equals k over L, some positive number, which I don't know, but somewhere here, the slopes are again 0. In between these two values, so if p is smaller than k over L but greater than 0, the slopes will be positive. So we'll have some positive slopes here. This is a quadratic polynomial, so the maximum will be actually really halfway between 0 and k over L, but never mind. If you draw it, you'll see positive slopes in this region. It will essentially look like that. This negative region is not relevant for us much because that's negative population, so we don't even have to think about that. But above k over L, that's relevant. If you're above k over L, then p is of course positive, but k minus L over p is negative, so you have negative slopes here. And it's even more negative if you go up. Okay, so this picture kind of tells us what the population dynamics is going to be like. If you start somewhere here, it will increase first, then it will decrease towards this asymptotic value. Sorry, not decrease, but will increase with a smaller derivative. So all of these curves will be asymptotic to p equals k over L. If you start above this critical value k over L, population will decrease towards this value, again asymptotically. So we didn't solve this differential equation, but we see that in all cases, population has a limiting value k over L. So we could deduce this even without solving the differential equation, just from the direction field. So these constants in this equation are quite important then. Their ratio tells you what the limiting population will be, some physically interesting quantity. Okay. Now let's think about an example of a different type. Suppose this is about interest rates. So you have some money in the bank, let's say, it's gaining interest. So money is compounded at certain times. Well, you know from daily life that this compounding could be at different times. For example, it could be yearly or monthly or even weekly, daily, and so forth. For example, how would you calculate if your interest compounding is monthly? That you first divide the yearly interest rate to 12, then you find the monthly compounding amount, and you multiply your original investment with a factor relevant to this interest rate. Now, this compounding could be theoretically made continuously, so done every second or millisecond or whatever. So we assume that's ideal case where the compounding is done continuously. So suppose that our savings account initially contains $1,000, and assume that money is compounded continuously, with the same interest rate, it doesn't change. Let's make this into some problem. Let's assume that the amount of money in this account is 2,000 liras at the end of the second year. The question is, what will it be at the end of the fifth year? Oh, 5,000? No, that's wrong. Okay. So it's much more complicated. So let's TB time, and let's say MT is money in the account at time T. Okay, we have a differential equation. So the rate of change of the money is proportional to money already in the account. The more money you have, the more interest it gains. Well, if you had a monthly compounding, you wouldn't have the derivative here. You would have, money after 1 month and minus initial money over the time interval. So this will be a difference over time interval. And the right-hand side would be, again, some factor times m. But now we take those time intervals to 0. I mean, the compounding is done continuously. Therefore, this part turns into a derivative. But the right-hand side is, again, the existing money times some number, which we don't know yet. Okay, if we solve this differential equation, this is a very similar equation to the population dynamics example. It's again an equation of the same type. Let me not repeat the steps. This is separable, and the solution gives you your initial money times e to the power this constant times t. So it's a growing exponential times a constant, where this constant is the initial amount of money. We know that m0 is 1,000. That was given in the problem. Now, we were also given one more piece of information, and that was m2 equals 2,000, right? Now, that should be equal to m0 times e to the 2k. So when t is equal to 2, that's what the right-hand side is, so we should have this equality. From here, you can find k. E to the 2k is 2, therefore k is ln2 divided by 2. Okay, now we have everything to calculate whatever we want. Now we want m5, right? So this is going to be 1,000 times e to the, now we know k, so ln2 over 2 times 5, t is 5. Well, you'll need a calculator here. So if I'm not wrong, this gives you something like 5,656 0.8 liras or something of that sort. Okay. Now, as a final type of example, let's look at some container problems or so-called tank problems. We are calling it a tank problem, but this is kind of relevant wherever you have some container. Your container could be an ocean, a lake. It could be some body parts like a liver or a kidney, and this is also used in medicine. Okay, but we'll suppose that we have some tank with some tap where liquid can leave here, and also liquid goes in here. So, okay, I'll make up some numbers. So suppose, say at time t equals 0, the tank contains 50 kilograms of salt dissolved in 1,000 liters of water. Okay. Now we assume something about both this entering part and exiting part. So assume that water containing 100 grams of salt per liter flows into the tank. Flows into the tank at a rate of 30 liters per minute. Okay, suppose the tank is mixed well, so and let me continue. The well-stirred solution leaves the tank at the same rate. And the question is, find the amount of salt in the tank at any given time. Okay, so this was a long text, so let me try to diagrammatize this. So you have something like that. Initially, you have 1,000 liters and 50 kilograms initially. What else are we given? We have some incoming solution. Well, the flow rate is 30 liters per minute. That's the fluid. And how dense it is, how much salt do you have? It's 100 grams per liter, right? So these are two different quantities. One is amount of salt per liter. The other is how fast it goes in, 30 liters per minute. Now, what about this exiting Great. We also know that this is 30 liters per minute. And how many grams per liter, we don't know. And that's the whole point. The amount of salt in the tank will change in time. Therefore, how much or how many grams per liter you have outgoing here will also change in time. This is not a constant. This question mark is something that's going to change in time. Now, let's try to be a little bit more specific. Let T be time and Qt the amount of salt in tank at time t. We cannot compute Q directly. It's not an arithmetic problem. That's important to realize. It's difficult to write down Q directly, but it is easier to understand how fast it changes. So let's look at its derivative instead. Okay, so this is the rate of change of Q. It is rate of change from the incoming side, let's call that rate in, and the rate of change resulting from this outgoing part, rate out. Okay. Well, the unit of Q is grams, and the unit of T used in this problem is minutes. So in this equation, everything should be at the end grams per minute. Okay, that's important. Now, how do I really write rate in and rate out? Rate in should be quite easy. Now, in the incoming side, everything is constant. It is 30 liters a minute with every liter carrying 100 grams. So you should multiply these two quantities, 30 liters per minute times 100 grams per liter. So you can do also cancellation in units. This liters will cancel, and the overall unit of this quantity will be grams per minute, which is correct. This was rate in. Now, how about rate out? I still have the 30 liter per minute, but how many grams per liter? Well, that changes, and this is going to be a function of T. What exactly it is? I want to find sort of density of salt. So it should be how much salt I have at time t in grams divided by the total volume, which is 1000 liters. So if you have Qt grams in the whole tank, and the tank contains 1000 liters all the time, the volume doesn't change in this problem, then in 1 liter you would have this much, Q over 1000. In this sense, we now see that this is not a calculus question, it's not an arithmetic question, it's a real differential equations question, because both on the left and on the right you have Q. Okay, now let me simplify. 3000 minus, now this is 3 over 100 Q. Okay. Now, okay, then how do you solve this problem? Well, this is a separable equation. So you can do the usual tricks. Q over Okay, maybe it would be easier with kilograms rather than grams, but anyway, we started this way. If I equate denominators, it's like 300,000 or 3 times 10 to the 5 minus 3q equals integral dt over 100. I guess that should be correct. Okay, this side gives us minus 1 over 3 ln 3 times 10 to the 5 minus 3q, and this should be equal to t over 100. I also have to put a plus c. Then you can solve this equation for q. You exponentiate and you leave q alone. Let me just write the final answer. It should be 10 to the power 5 plus t times e to the minus 3t over 100. This c is different from the c above. When you exponentiate, this will become e to the power c, and you rename it as c. Please do it yourself as well. And what was q0? Q0 was 50 kilograms, so 50,000 grams. And if you plug this value in, you'll be able to find c, 5 times 10 to the 5 equals 10 to the 5 plus c e to the 0, which is 1. So c is 4 times 10 to the 5. And here's our final answer. Okay, it's this many grams. Let's double check. At time equals 0, you have 5 times 10 to the 5, which is 50 kilograms. And eventually, when t goes to infinity, this decaying exponential part will go to 0, and the limiting value will be 10 kilograms. That's kind of consistent, I suppose, because the incoming solution had a density of 100 grams per liter. If you had 1,000 liters purely of that solution, 1,000 times 100 grams per liter is really 10 to the 5 grams. So after a very, very long time, you have very little of the initial solution left, and almost everything is composed of the incoming solution. So it is natural that has density very close to 100 grams per liter. Okay, so this answer looks correct. Okay, so we saw several examples of first order models today. This was all. Thank you very much.